Okay, so let's talk about Chi-Square. On Sunday, I'm going to do another review session. I'll put it up so that it's really intended for another class. It's mostly a review of hypothesis testing and t-tests and so on and so forth. Paired samples, independent samples, and so on. So I'm going to mostly be covering that on Saturday or Sunday. I'll post the time and date. Probably Saturday. That's a bad day. It's going to be raining on Saturday. I think Saturday morning's a good day to do it. So it'll cover that. So today I'm going to spend most of my time on Chi-Square since we've introduced that. And for the guys in Bio 610 and 610, it's going to be on the exam. So we want to make sure that we understand it. Okay, so here's a file from the homework problem. And you'll notice that this has 52 people that use hot air dryers in a bathroom, 46 people that used paper, and we're trying to determine whether or not it's more or less likely that they're, say, going to come down with the flu this season. So this might be historical data that an employer kept from last year or something like that. Okay, so let's take a look at this. How many people did he actually survey, or how many people were involved in this? Well, it looks like there was 46 and 52, which is 98 people involved, right? Makes sense? Out of those 98 people, 29 of them got sick, got the flu, and it looks like 69 of them didn't get sick, right? Right, that adds up to 98, right? So we're okay, right? There's an echo? Oh, my goodness, okay. Tell you what, maybe it's from this. How about now? It's better now? Okay. Yeah. Okay. Let's see. There was some other way I managed to. Maybe I can kill it over here. I think it should be gone now. How's that? Okay, good. All right. So at any rate, so we wound up with 98 people. 29 of them got sick. 69 of them didn't get sick. 46 of them liked using paper, right? And this is a total. And 52 of them like using those hot air dryers in bathrooms. So we're speculating maybe it has something to do with the rate that people would get sick. Of course, this is all conjecture. It's kind of fake, right? So let's take a look at this. First of all, if we look at this, just the way this happened, let's say that I didn't see this at all. All I saw was that there were 98 people. Of those 98 people, 29 of them wound up getting sick. Okay? And I know that 52 people, whoops, hit escape. I want to change that to 52. 52 people use the hot air dryers, and 46 people use the paper towels. Okay? Let's say that's all I knew, right? So 29 out of 98 employees got sick. So what's the prevalence of flu in this group? How many people, what is the incidence really, but say prevalence of flu in this group based on the fact that 29 out of 98 got sick? Right? It's just prevalence is equal to 29. Whoops. 29 over 98. Whoops. Equals 29. Hang on a second here. Equals 29 over 98. That's about 30, a little less than 30%, right? So that's the prevalence. So now let's look at this table. 30% of this group got sick, right? Okay, so now I don't know who's using whether or not one person's using. At this stage, I don't know who used what, paper or towels or whatever, but I'm going to take a look at this. 46 people used paper towels instead of that noisy, nasty hot air dryer, right? If I knew nothing else, all I knew is 46 people used the paper, and the prevalence is about 30%. How many of those 46 people would I expect to get sick? Yeah, about 30% of them, right? So I could calculate the expected number of sick people as being equal to 46 times, and I'm actually going to use this number rather than round it off because I don't like rounding off until the very end. Okay, so about 13 and a half people out of the 46 is what I would expect to get sick, right? If there is no difference between the hot air dryers and the paper towels. Well, how about the 52 people that use the hot air? Well, I said there was no difference, so I would expect 30% of them to get sick too. So 30% of them is equal to 52 times 0.295, 0.296. So I would expect about 15.5%, 15.5 of them to get sick. Notice I have fractional people. Usually in real studies, you don't have fractions of people, right? So what does that leave in terms of who didn't get sick? Well, it's going to be equal to 46 minus 13.6 among the people that use paper towels. And this is going to be equal to 52 minus 15.38 for the people that used hot air. Okay? These are my expected values. If there's no difference between the rate at which people that use paper and the rate at which people used hot air got sick, I would expect 29% of each group to get sick. And that's what this table should look like. Now, let's go and take a look at what it really looks like. Turns out, when we actually surveyed people, which one did you use? And did you get sick? Turns out that we got 19 people out of 46. We got more than we expected that got sick that used the paper towels. And look, with 10 people out of 52, we got fewer people that use hot air that got sick than we would have expected if there was no difference between using hot air and paper towels, right? So there's a difference between our observed values and our expected values, right? And that difference may be a clue to what's going on here. So that's what we're going to analyze now. And the way we're going to do it is that there's a statistic for doing this. And the formula for that statistic, chi-square, is equal to, well, since there's a difference between what we observed and what we expected to see, since there's a difference, let's see how big that difference is. The bigger the difference is, the more likely it is that our original premise that there's no difference between using hot air and paper towels is wrong, right? Bigger the difference is, the more likely that there is some kind of an association between getting sick and how you wash your hands, right? So if the difference is small, that could just be due to chance. If the difference is bigger, then that's less likely to be due to chance. So what's my null hypothesis here? My null hypothesis is that there's no difference between my observed values and my expected values, right? Well, that's already not true because, see, there's a little bit of difference. It may be due to chance. So let's phrase that a little bit differently. Let's say our null hypothesis is there's no association between what type of drying, how you dry your hands, and whether or not you get sick, right? And our alternative hypothesis is that there is a difference between the two, right? And so we want the probability of incorrectly rejecting the null hypothesis. In other words, saying that these two things are different, these two outcomes are different. We want the chances of us being wrong if we say that they really are different to be less than 5%. So we want this chi-square statistic to be a big enough number that there's less than 5% chance that you would get that big a difference and have no difference and have that occur by chance, not due to some real difference between which way you cleaned your hands and so on, right? So, okay, so we're going to actually calculate that. And how do you calculate it? Well, since we're looking at the differences, we're going to take each difference, right? So we're going to take the difference between paper towels and number of sick people that we observed and the number of sick people that we expected. Observed minus expected. That's equal to our observed values minus our expected values, right? And that comes out to that. Okay, then I'm going to go back here. Well, how about this one? Hot air people, how many sick versus how many sick hot air people down here? There's a difference there. Okay, so let's take the difference there. That's equal to that minus this. Okay, and I'm going to do the same thing. Notice what's going to happen here. What's going to happen here? Same thing as when we were working with the differences between the mean and each individual value, they're all going to wind up canceling out, is equal to 27 minus this number, and this is equal to 42 minus the expected value. Notice also that the expected value is fractional, but the observed values are always whole numbers because they're actual people that we're counting, right? Okay, so now if I add up all the differences, they're going to cancel out. It's going to be zero. It's always going to be zero because whoever's not in one box is going to be in another box. So we can't tolerate that. We need to get a number that represents the differences, how big the differences are. One way that we could handle this is just look at the absolute value. Just ignore the negative sign. Just add up all the absolute values. Statistics, that's too simple. We're going to do it a more difficult way, right? We're going to square each one of these numbers. Okay, so we're going to take this one, which is the observed minus the expected value, right? And I'm going to multiply it by the same thing, right? Okay, I'm going to put parentheses around there. Actually, I can actually go over here and do a little, I can put a caret there and square it. And that should square it. Now it's squared. Okay, I'm going to do the same thing with this one. Put parentheses around it. Put a little up caret, which means a power, squared. That one squared. I'm going to take this one. Okay. I'm going to take this. And I'm going to say caret and square it. Okay. And then I'm going to take this last one. I'm going to do the same thing. I'm going to square it. Caret up and square. Okay. So now I squared them all. So now I can add all these together. And the bigger the differences are, the bigger the sum of these numbers is going to be because they're not going to cancel each other out now. The next problem I got is that I've taken these numbers, these differences that were small numbers, and by squaring them, I've made them enormous numbers. So I want to get them back into the range of the numbers I was working with. So what I'm going to do is I'm going to take this, let's say observed minus expected, I'm going to square it, but then each box I'm going to divide by the expected value. And that'll bring it back down into the range of numbers that we were dealing with. So for this one, right, I'm going to divide by, and what's the expected value here? The expected value here is this number here. Okay, and that's the number we wind up with. Well, how about this box? I'm going to divide that by the expected value for that box, which is this number. And how about this one over here? Whoops, this one over here. Divide by the expected value for that box. And I'm going to do it one more time. Divide by the expected value for that box. Okay, so now I've taken each one, now notice sum of, right? I'm taking each one of these boxes, performing this operation, taking the observed value for the box minus the expected value for the same box and the expected values, squaring the differences, and then dividing by the expected value. And then I'm going to take the sum of all of them. So the sum is going to be equal to the sum of all of these. Oops. So that's my chi-square value, 3.02. Okay, so now, if that were a t-square, that would be a great number, right? But it's a chi-square value, so we use a different table for chi-square value. There's a chi-square distribution, and I'm going to show you a chi-square table now. Okay, table. Okay, let's open that table up. And here's what the chi-square distribution looks like. I think there's a picture there that's missing. Did I lose the picture somehow or other? Was it in the original? No, it wasn't in that. Wasn't in that document, right? Not in that one either. Oh, take my word for it. What does the chi-square distribution look like? The chi-square. Yes, I'm sorry. What's that?
I was going to answer the question.
Oh, sure. Go ahead. What's that?
So degrees of freedom would be 1 to 2 by 2 table.
Right.
And we do the number of rows minus 1 times the number of columns minus 1.
Exactly.
And that would give us 3.8.
Exactly. Okay, that's our critical value of chi-square. Now let me just repeat that for the guys that are online. The number of degrees of freedom when you do a chi-square calculation, chi-square statistic, is the number of rows minus 1, 2 minus 1, 2 rows, times the number of columns minus 1. 2 minus 1 is 1. Multiply them together. 1 times 1 is 1. So it's 1 degree of freedom. Now you can do chi-squares with chi-square with 3 rows and 2 columns, or 4 rows and 5 columns. Do anything you want, but you have to use a different number of degrees of freedom because there are going to be more boxes you're going to compare. So the numbers are going to be bigger just by virtue of the additional calculations you're going to do. So in our case, our chi-square value, our critical chi-square value is 3.841. In other words, we want that chi-square value to be big, because when that chi-square value is big, it indicates the differences between the observed values and the expected values are large. And the larger they are, the more likely that we can reject our null hypothesis. As it happens, that number 3.841 is the exact value of chi to have 5% chance you would be wrong in rejecting the null hypothesis. So anytime you get a value bigger than that, you can say to yourself, there's less than 5% chance I'm going to be wrong if I reject the null hypothesis. So we want the chi-square value to be bigger than that. So what was the chi-square value that we calculated? 3.02, right? Is that chi-square value bigger than that? Remember, what do we call that value again? Because it's so important, the critical value of chi-square. So our calculated chi-square value is not bigger than the critical value of chi-square. So in this case, we fail to reject our null hypothesis. We're not always going to win, right? Some days you go out there, you play 9 innings and you win. Some other days it rains, and some other days you lose, right? Today we lost, right? It is raining out there. Was it raining earlier? No, yesterday. Okay, so at any rate, yes, we got the game in anyway. Our chi-square is 3.02. The critical value of chi-square from the chart that we need to be bigger than in order to reject the null hypothesis is 3.841. Exactly. So we fail to reject the null hypothesis. Remember, the bigger that number is, the bigger the difference between the expected values and the observed values, and the less likely that that difference is due to chance. Okay, so that's what we want. We want a big enough difference to say it's not due to chance. Then we could reject our null hypothesis and say the null hypothesis was there's no association between how you dry your hands and whether or not you got sick. The alternative hypothesis is that there is. Had this been 4.1, let's say, we would have rejected the null hypothesis that there's no association and accepted the alternative hypothesis, and then all of us would have gone in, and from now on we would have washed our hands with the blower instead of the paper towels, and we'd be like, we'd be flu-free but deaf, from those things. They're like, like the rocket engine, some of them, right? So that's the deal here. That's what we're doing. Now, there's another things that you can do with a 2x2 chi-square, with a 2x2 contingency table. These are called contingency tables. The other thing that you can do with these tables is that you can describe the relationship between the different exposures, paper towels or hot air, another way. One way is to describe it as a risk. Okay, so in other words, for the people that I did, now I'm going to go to the observed values for this, because the risk is going to be exactly the same for the expected values because they're based on the same prevalence, right? So if you want to calculate, you could actually do this later, right? So the risk of getting sick if you use paper towels in this population was equal to 19 out of 46 people. So 41% of the people that used the paper towels got sick. That's your risk of getting sick. What about the people that use the hot air? Okay, well, the risk for them was 10 over 52. How many of them got sick? 19% of them got sick. Well, that's pretty interesting. Well, you know what I'm going to do? Look, the 41% versus 19%. Almost twice as many people got sick. Twice the percentage of people got sick that use the paper towels as the hot air. I'm going to take advantage of that. That's a convenient way for me to express the comparison of these two risks. I'm going to say the relative risk, or sometimes called the risk ratio, ratio is one number divided by another, is equal to 41% divided by 19%. So the risk ratio, oops, I don't know why it said that. The risk ratio is 2.14, 2.15. You're 2.15 times as likely to get sick if you use the paper towels instead of the hot air. I won't even go into those people that don't wash their hands after they go there anyway. So we don't want, we're in public health. We're not going to talk about that, right? So at any rate, but isn't that a convenient way to describe this? Your increased risk. In other words, that's where these things come from. Your increased risk if you're for lung cancer, if you're a smoker, is 5 times if you're a non-smoker. How do you get that? Well, you compare how many people that smoke, what the rate of lung cancer was in people that smoke versus rate of lung cancer in people that don't smoke. So if the rate of lung cancer, not everybody that smokes gets lung cancer, right? They die from other stuff, right? So maybe the rate of getting lung cancer if you smoke is 10 in 100, right? But if the rate of lung cancer is, if you don't smoke, is 2 out of 100, then 10 out of 100 is 10%. 2 out of 100 is 2%. 10% divided by 2% is 5 times the risk. That's where that comes from. Now, in statistics, very frequently, instead of using risk ratio, to be honest with you, I kind of find risk ratio a little bit more intuitive, but most studies use something called odds ratio. Okay, the odds ratio is calculated a little bit differently. The values come out very similar, but they're just calculated differently. Okay, and how do we calculate the odds? Well, instead of saying 19 out of 46 people that were involved, we say, what's the ratio between the number of sick people and the number of people that were not sick? That's the odds, right? Okay, so it's going to be equal to 19 divided by 27. The odds for sick versus not sick for that population was 19 to 27. Right? So that would be 0.70. The odds for people that used hot air getting sick within that group is equal to 10 versus 42. 10 out of 42, about 1/4, 23%. The odds ratio is equal to, again, since it's a ratio, we just divide one by the other. Okay, and that comes out to be 2.9. It's about 3 times greater odds. Now, it puts you in the same ballpark. I mean, it's, you wind up with a different number, but it's a different way of expressing this relationship. That's our odds. Now, let me ask you something. If there were no difference between the rate at which people got sick that used paper towels and the rate at which people got sick that used hot air, well, then the risk would be the same. So what would the risk ratio be? Be equal to 1. Both those numbers would be the same. How about the odds ratio? Right? What do you expect the odds ratio to be if there's no difference? No, 1 also. Yeah, because the odds here would be the same as the odds here. So when you divide one number by the same number, it's going to be 1. So it's going to be 1. Problem with that is that let's say that it did come out 1. Well, with chi-square, at least we had a table where we could go to where we would know what's the probability that we would be wrong if we reject the null hypothesis. We would have a place we could go to where we could say, oh, it's less than 5%, so I can reject the null hypothesis. Well, how do I do that with risk and with odds? Well, since I know that my expected value is 1, right? What you can do is you can calculate a confidence interval for the risk or for the risk ratio or for the odds ratio. And in order to say that the risk ratio or the odds ratio, let's just focus on the odds ratio, in order to say with 95% certainty, 5% chance of being wrong, that the risk ratio or odds ratio is not 1, what would that confidence interval have to not include? 1. If it doesn't include 1, you can say with 95% certainty that it's not 1, right? So now we would have to, in order to calculate the confidence interval, these are proportions. You'd have to go and use that complicated proportions formula. I'm not going to ask you to do that on, say, a test or on a homework or something like that. Instead, you can calculate chi-square very neatly using Excel or whatever, even a calculator pretty easily, just as we did now, and then look it up on the table. But for odds ratio and relative risk, it's easy enough to calculate what they are, but to calculate confidence interval, I'm going to let you go to SPSS to do that. So I have this on Blackboard. I didn't put it up immediately because I figured To be honest with you, I wanted to encourage you to like import the data into SPSS yourself, but I got a lot of crabbing about it, so I posted the SPSS, the .sav version of the file, so it's up there now. So I'm going to go to SPSS. Okay. I'm going to open SPSS. I'm going to open the same file in SPSS. It's going to have a somewhat different format in SPSS. There's two variables here, so there's going to be two columns. One column is going to be what kind of dryer you used. The other column is going to be whether you got sick or not. So variable one is a dryer. Variable two is whether or not you got ill. Okay, so I don't need that. I'm going to go File, Open, Data. Okay, there's that file. I'm going to open it up. Okay, and it pulls up that page. So here, take a look at this. The dryer, paper, or whether each person, like for instance, this person used paper and didn't get sick. This person used hot air and did get sick. This person used hot air and didn't get sick. So these are all the individuals in this study. Notice there's 98, just like our file before was. In fact, I can go up to Analyze. I can go into Descriptive Statistics. We're back using Descriptive Statistics. And I'm going to climb down here to something called crosstabs. Those tables that we use, sometimes you call them contingency tables, sometimes you call them crosstabs. So I'm going to open up crosstabs, and I'm going to tell it, well, what's in the rows? The rows is usually you put the exposure, the type of hand dryer, and in the columns you usually put the outcome, like if there was disease or not. So you're going to put that into the columns. Now notice a whole bunch of buttons I can press here. So for instance, in cells, I can tell it to give me the observed values. I'll just do that. I'll do that right now. And just that. That's the only thing I'm going to do. And sure enough, there's our table, just like we had it before, just like we had it in Excel. Now, what about the expected values? Did you notice that when I went to Analyze, Descriptive Statistics, Crosstabs, and I went into Cells, that another choice was expected values. I'm going to click OK, and what do we wind up with there? Well, it doesn't give me two separate tables, but it gives me for each box, it gives me the observed value and the expected value, observed value and expected values. It rounds them off here. It really has in its memory, it really has the whole thing. It hasn't rounded them off. But to make the table convenient, it rounds them off. So there's the various numbers that we just calculated. I hope it's right. I hope we did it right? So now let me take a look at this another way. Analyze, Descriptive Statistics. And you guys, when you get a chance, you can slow this down. You can play this back and slow it down. Crosstabs. And I'm going to go into Cells. This time I'm going to turn off expected values. I'm going to turn on, give me the percentages by rows. I'm going to say continue. Okay, now let's see what it gives me now. Well, now it gives me 41.3% and 19.2%. Well, that's what we did before. Wasn't that the risk that we calculated before? So that's how we got that relative risk, 41% divided by 19.2%. Right? So it's giving us, depending on what choices we choose under these buttons, it gives us all that information. Well, now let's go ahead and do this, the whole Megillah. Let's actually calculate the chi-square and the odds ratio and relative risk. So I'm going to go to Analyze, Descriptive Statistics, Crosstabs, and I'm going to go in here and I'm going to say Statistics. I'm going to ask it to calculate the chi-square and the risk. By risk, it's going to do both. It's going to do relative risk, and it's also going to do the odds ratio. Okay, I'm going to click Continue. Then I'm going to click OK. Let's see what we wind up with. Okay, so let's take a look at this. So I calculated here's our various risks and so on and so forth. Well, let's take a look over here. So you want to know something? Right? I think we made a mistake when we calculated the chi-square. Uh-oh, did I calculate the chi-square? Yeah. Yeah, you want to know something? We must have made a mistake. Let's go back. Let's go back here. So anybody see where we made a mistake? hang on a second. First of all, let me check to make sure all these numbers are the same. 19 and 10.
Right.
Oh, it's the tables, right? Yes.
So I actually did this one and I got the prevalence. I did and they know that was calculated because prevalence is different for the one that you use here. I rounded it up.
Yeah.
All the other answers for the
Yeah, rounding shouldn't, I mean, you really shouldn't round until the very end.
Yeah.
However, that's not what the problem here. The chi-square is completely different. Hang on a second. I must have made a mistake here. Let's see. Let's see where if we can catch a mistake here. So this is B3 minus B10 over B10 squared over B10. I think there's something wrong with this number here. Let's see what that number is. That's C4 over C11 divided by squared and divided by C11. Yeah. That's B4 minus B11 squared. Hang on. Let me just go through these so I can see what I got wrong here. This one. C3 minus C10 squared over C10. And if I add all this together, let's see, there's something wrong here. Equals the sum, parentheses, of all of these. There we go. Hey guys, I must have missed a box. When I did the sum and I circled the boxes, I must have missed a box. It's 5.7. That changes things a little bit, right? The first thing it changes. I can what?
Whether you
I can reject my null hypothesis now because it's more than 3.84. What? Yeah, what's the other thing that it changes? It makes it the same as what we got here, right? 5.7. Okay. Now, there is something here called a continuity correction, and there's something called the Fisher's exact test, right? That continuity correction, when you have one of those boxes has 5 or fewer people in it, well, that introduces this, or like there's relatively few people in this study, that introduces a special kind of error, right? That you have to make up for. For our purposes, I'm going to ignore that for now. We'll talk about that after the exam. Like for now, just use the simple chi-square formula. I'll make sure that that whatever examples we do doesn't involve something you really need continuity correction for. We'll talk about that later on. Okay, but they come out the same now, don't they? Right? Chi-square. How come you guys didn't catch that? I mean, look how obvious it is, right? We had to add those together, right? The sum of all those 4 box differences, square, and then divided by each other. We got 2. We got almost 2 here. That's 4 all by itself. Couldn't have been 3, right? Then we got 1 and 1 here, so it had to be 5 something, right? So anyway, I should have caught that myself too. But those are the breaks. Sometimes, we learn something. Right? Sometimes by getting stuff wrong, you learn a bit more. So anyway, what else do we have here? We also have, let's see, let's go down here, the risk estimates, right? Well, let's see, odds ratio for a hand dryer used versus paper versus hot air. And the value was 2.956. That's the same one we calculated when we did it, the odds ratio, right? But look what it gave us here. It gave us the 95% confidence interval for the true value for the population of the odds ratio. And what was it? 1.195 to 7.3. What's not between those two numbers? 1. So we're 95% certain that it's not 1, which would have told us that there's no difference, no association between which kind you use and whether you got sick or not. So that also tells us you can reject the null hypothesis. Now, for that, you could use the null hypothesis that the odds ratio is equal to 1 is the null hypothesis, and the odds ratio is not equal to 1 is the alternative hypothesis. And then you calculate your confidence interval and make sure 1 is not in there somewhere. And if it isn't in there, you reject your null hypothesis that it's equal to 1 and accept your alternative hypothesis not equal to 1. Okay, so what about the risk ratio? Well, our risk ratio is here, 2.141, right? That's what we calculated for the risk ratio, 2.15 roughly, right? So what about that? The 95% confidence for the risk ratio is also doesn't contain 1. So all three of these things agree we can reject the null hypothesis. Okay, so that's pretty much where we stand with this stuff. Like I said, I'm staying away from this idea of the continuity correction for now, until next week, till after we do the exam, because I just introduced this idea of chi-square. Now, I'm gonna have to shut down this computer and go over to the other machine because I'm going to run out of power here. I don't have my power supply with me.